So 17x1 that is equal to 0, okay, and x2 is now free variable. So take x2 is equal to k and x1 is equal to 0. So what is our eigenvector corresponding to lambda is equal to minus 16, that is 0 1, okay. This is our eigenvector corresponding to lambda is equal to minus 16. So that's why here we written that similarly we can find eigenvector corresponding to lambda is equal to minus 16. So the eigenvector corresponding to lambda is equal to 1 is 1 0, and similarly the eigenvector corresponding to lambda 2 is equal to minus 16 is 0 1, okay. So that's why here we written 0 1, that I explain here. Now taking x1 x2 as column, a matrix P can be formed as P is equal to x1 x2, that is equal to 1 0 0 1, which is orthogonal matrix, correct. Now the diagonal matrix D, that is equal to P transpose AP, that is equal to 1 0 0 minus 16. So using the orthogonal transformation x is equal to px dash in equation 1, we obtain px dash transpose A px dash plus k px dash minus 256, that is equal to 0, okay, in equation 1. So see, this is our equation 1. In this equation 1 we put x is equal to px dash, okay. In this equation 1 we put x is equal to px dash. So here is our equation, and now simplify this equation, x dash transpose and this p transpose with multiply with AP, so p transpose AP x dash plus kp x dash minus 256 is equal to 0, x dash transpose dx dash plus kp x dash minus 256, that is equal to 0 also. So this was equation 2. Now kp is equal to 8 128 1001, that is equal to 8 128, okay. So hence 2 can be written as with this notation x dash y dash 100 minus 16, that is equal to x dash y dash is a column matrix plus 8 128 x dash y dash minus 256, that is equal to 0. So put all these values, so x dash square minus 16 y dash square plus 8 x dash plus 128 y dash minus 256, that is equal to 0, and then x dash square plus 8 x dash plus 16 minus 16 into y dash square minus 8 y dash plus 16 in bracket minus 16, that is equal to 0. So finally we get x dash plus 4 whole square minus 16 y dash minus 4 whole square, that is equal to 16. So now we translate the coordinate axis using the transformation x double dash, that is equal to x dash plus 4, and y double dash, that is equal to y dash minus 4. So hence 3 can be written as x double dash square minus 16 y double dash square, that is equal to 16, which is a hyperbola. So this is the equation of hyperbola, and here to complete the solution of this question. Now next question, question 7a, the first part. Find the standard matrix for the stated composition of linear operators on R2. A rotation of 60 followed by an orthogonal projection on the x-axis followed by a reflection about the line y is equal to x. Now just try to understand that what is the meaning of this rotation of 60 followed by an orthogonal projection on the x-axis, right? So definitely we have to the composition of 3 transformation, right? First one is rotation, then orthogonal projection, and then reflection about the line y is equal to x, okay. So first of all, this is the rotation. Now already we have the standard matrix for the rotation matrix, some angle with some angle theta. So that standard matrix that you have to remember. And then orthogonal projection on the x axis, that is also that standard matrix. So just try to understand that how create this standard matrix and how we compose it the three matrices. Okay, so just try to, and then the next question is we have to use a dilation with factor k is equal to 2, followed by a rotation. Again the rotation is effected here, and then followed by a reflection about the y-axis, So just try to understand. I will explain you that some of the standard matrix how we used it. So let's see. Okay, so let's take R2. So this is our vector xy, call it xy in R2. When we take orthogonal projection on x axis, so that vector become now x0, right? So what is the standard matrix for this vector? So definitely this is a transformation, right? T of xy is equal to x0. So this is a linear transformation, and definitely we can find the standard matrix for that transformation using the some basic portion of the linear transformation. So this is x0, right? So what is the standard matrix for this T of xy, that is equal to x0? And just try to understand that this is orthogonal projection on x axis, right? So consider the first element x, and what is the coefficient of x and y in the first coordinate? 1 0. So that's why here we written 1 0, and this is second coordinate 0. So definitely the coefficient of x and y in the second coordinate, that is 0 0. So this is the standard matrix of the orthogonal projection on x axis of the vector of R2, right? Now similarly, if we take, let's take another figure. If we take, this is our vector xy, this is our line x is equal to y, right? This is our line x is equal to y. So when we take reflection of the vector xy about the line x is equal to y, so in that case our new vector is become yx, correct? Our new vector is become yx. So that's why you can see the standard matrix for the reflection of the vector xy about the line x is equal to y, that is, what is our standard matrix? I just written down all the roughly here, right? So that you can understand that one. So y is this is y. So in the first coordinate, what is the coefficient of x and y? That is 0 1. So 0 1, and the second coordinate, the coefficient of x and y, that is 1 0. So this is our standard matrix for the vector xy, okay? And then dilation, that is for dilation we know that T of xy is equal to kx ky, but here we have to mention that dilation with factor k is equal to 2. So definitely our standard matrix is 2 0 0 2, because basically this is k 0 0 k, but already mentioned in the B part of this question that dilation, we have to use dilation with factor k is equal to 2. So that's why our standard matrix for that operator, that is 2 0 0 2. okay, and reflection about the y axis. What is a reflection about the y axis? Just try to understand that one. Reflection about the y axis. So this is vector xy. Now reflection about the y axis. So this is our y axis. So reflection about y axis of the vector xy, that will become minus x y, okay, and the standard matrix for that vector, for that linear transformation or linear operator, that is definitely, now you can understand, this is minus 1 0 0 1, okay. So that's why we use all this standard matrix, and then composition, using that composition we can find our new matrix, okay. So just try to understand that one. So the first part is, first of all, rotation of 60, and this is the standard matrix for the rotation, cos theta minus sin theta cos theta, and we have to use theta is equal to 60. So that's why cos 60 minus sin 60, sin 60 and cos 60. This is our first standard matrix along the rotation of 60. So put all this value, cos 60 and sin 60. We know that cos 60 is 1 by 2 and sin 60 is root 3 by 2. So put all these values. So this is our T1, first matrix of 2 cross 2. Then T2. This is our T2, which I explain here. What is T2? The orthogonal projection on x-axis, right? And this is a standard matrix for the orthogonal projection on x-axis of the vector xy. So we know that T2 of xy is equal to x0. So x0 can be written as, in this standard matrix, 1 0 0 0. So this standard matrix is coming from that one, right? So and T3 is what? The reflection about the line y is equal to x. We know that the reflection about the line y is equal to x is T of xy is equal to yx, right? So for yx, this is our standard matrix T3. The first for y, the coefficient of y, the coefficient in first coordinate y, and the xy, that is 0 1, right? And the second row is coming from the x, and the coefficient of in x, the coefficient of x and y, that is 1 0. So second row is 1 0. So now we have to find the T3 composition with T2 composition with T1. So definitely that is a matrix multiplication. First one is T3 0 1 1 0, second one is T2, that is 1 0 0 0, and third one is T1, 1 by 2 minus root 3 by 2, root 3 by 2, 1 by 2. First of all, we multiply second and third matrix. So first matrix is as it is, 0 1 1 0. We multiply second and third matrix, so we get 1 by 2. The first element is 1 into 1 by 2 plus 0 into root 3 by 2, so we get 1 by 2. Then 1 into minus root 3 by 2 plus 0 into 1 by 2, so minus root 3 by 2. Then this 0 into 1 by 2 plus 0 into root 3 by 2, so that is 0, and 0 into minus root 3 by 2 plus 0 into 1 by 2, so that is 0. And then multiply with this two matrix, we get 0 into 1 by 2 plus 1 into 0, so we get 0. Then 0 into you can understand that how we multiply matrix multiplication, right? So that you should know, that matrix multiplication, that you should know. So 0 into 1 by 2 plus 1, 0 into root 3 minus root 3 by 2 plus 1 into 0, so that is also 0. And then coming pick up the second row of the first matrix, 1 into 1 by 2, and multiply with each column of the second matrix, 1 into 1 by 2 plus 0 into 0, so that is 1 by 2, and then 1 into minus root 3 by 2 plus 0 into 0, so you will get minus root 3 by 2. So here is a final, this is our final matrix, 0 0 1 by 2 minus root 3 by 2. So this is the complete the solution of the first part, A part, right? So a rotation of 60 followed by an orthogonal projection on the x-axis followed by reflection about the line y is equal to x. Next question is a dilation with factor k is equal to 2 followed by a rotation of 45 and followed by a reflection about the y-axis. So again, first of all the dilation, so that is 2002, which I explained, then followed by a rotation of 45. So again the rotation of 45, so just instead of this matrix we have to use, instead of 60 we have to use 45 in this matrix, and then reflection about the y-axis, so that is t of xy. Reflection about the y-axis is t of xy is equal to y minus xy. So the standard matrix for that one is minus 1 0 0 1. So here I written all the matrices. T is equal to T3, T2, T1, where T1 is equal to 2002, T2 is equal to cos 45 minus sin 45, sin 45 cos 45, and put all these values. So finally we get this matrix 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2. And T3, that is reflection about the line y is about the y-axis, so that is t of xy is equal to minus xy. That is the standard matrix for that one is minus 1 0 0 1, and then again we multiply each of these three matrices, T3, T2, T1. So that is minus 1 0 0 1. Second one is 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2, and this is 2002, that is equal to minus 1 0 0 1. So that is 1 by root 2. First of all we multiply second and third matrix, so we get 1 by root 2 into 2, so that is root 2. Then 1 by root 2 with 0 into 0 plus minus 1 by root 2 into 2, so again we get minus root 2. Pick up the second row, then 1 by root 2 into 2 plus 1 by root 2 into 0, so we get root 2, and then 1 by root 2 into 0 plus 1 by root 2 into 2, so we get root 2. Okay, now multiply these two matrices, we get minus root 2, root 2, root 2, root 2. Okay, so here is our final standard final matrix. The next question, question 7a, second part. Determine whether the function t from v